could say, one bromine is wedged and one's dashed. But to make life a lot simpler, we tend to just draw the bromines physically trans with respect to each other without the usage of planes if possible. So there's the generic backbone, we draw the bromines trans with respect to each other. And obviously one come up here, one come down here. We could have two different ways that these bromines could attach here. So that's how we get two different products here. But now we got to go back and assign some planes of orientation for our methyl and for our hydrogen. Now, before we turn this into a stereocenter, these methyls were on the exact same side of the structure. So when we transfer it over to our products, that means they both have to either both be dashed or both be wedged. Now I think if just for the sake of the answer key, he draws them both as wedged. But you could draw them both as dashed as well. And then we don't draw the imaginary hydrogens there. But again, the reason why these guys are both wedged is because they were on the same side of the structure before the bromines attached. That's not going to change simply because we add two additional functional groups. But yeah, that's basically the two we could have. And obviously we could draw the same structure but with both methyls being dashed instead of wedged. But does that make sense so far? Like I said, when you get an alkene, you're tossing bromine at it, you're getting both bromines attaching, but again, in the trans configuration. Because what you technically end up with, if I draw just the generic structure for an alkene, you end up with a weird and very, very ugly and very unhappy bromine molecule sitting in an intermediate like this. Basically, the alkene attacks the bromine, and you end up with this weird, ugly mess. But now notice this looks a lot like an epoxide. So notice that when the second bromine comes along, it's going to be negatively charged. It's not going to come in from the same side as the bromine that's sitting up here. Instead, it's going to come from down here and break this bond, and that's how we wind up with the, that's how we end up with the trans bromines. Not too bad, right? Like I said, you can treat it kind of like an epoxide, only with an additional step where the oxygen is the bromine sitting there, and it's very, very unhappy. But okay, and that's pretty much it for this one. So now we have to describe the relationship between them. So you basically have flipped the orientation of the bromines as well as the methyl group. So what happens to your stereocenters here? They're all going to switch. So how are these guys related? They're enantiomers. Yep. They're diacetyl enantiomers. But any questions on this guy? That's all you guys had to do for this one, is draw out the two possible structures, which again are just the inversion of each product, and then identify them as identical, diastereomers, or enantiomers. Any questions on this guy? Mm-hmm. Ah, good question there. So does bromine always replace hydrogens? So in this particular structure, the bromine is actually not replacing anything. The bromine is not taking the place of the hydrogens, they're actually still there. What ends up happening is you're actually, you're ruining that pi system is what you're doing. Because the double bonded carbon right here, these electrons come out and attack bromine. So they can now occupy an additional substituent, but sacrifice that, that pi bonding structure they have there. So no atoms got replaced or removed here, you just added bromines to this, but you lost this double bond right here, and now everything is single bonded. Good question there, right? Like I said, if you guys ever in doubt, be sure to draw out all the atoms and think to yourself, did anybody really leave here? And even if I didn't draw that there, we know there's only 3 bonds there, so that means that fourth bond has to be occupied by a hydrogen. Any other questions on this guy? Any other questions, thoughts, concerns? This is standard alkene and bromine pretty much reaction together. We call it bromination, but that just sounds like a horrible rash, but it's just an alkene with bromine being added to it. I know you guys are like, okay, what the fuck is this? What's this next part?
Yep.
That's MCPBA, which, if you guys are wondering, that is the structure of MCPBA drawn out. Now, just like DMF isn't drawn out and a whole bunch of other various solvents, this one is not going to be useful for us because you guys will never be asked to show the arrow pushing for this mechanism. What you guys have to know is what it does and what its overall goal is. Now, the big kind of hint / giveaway is to look at this cluster of oxygens right here. So what ends up happening is you add an oxygen to your structure, but you make a very, very specific kind of structure with it. What do you guys think it is? Yep, that's right. I heard the whisper, but what is it? Come on, you guys know what it is. I just heard it. What structure are we making here? So I heard an alcohol. So we are attaching an oxygen, but we don't have a proton donor. So we cannot make an alcohol from this. But what can we make that just tosses an oxygen into the structure? Yep, bingo. We're making an epoxide. We're making one of these. That's MCPBA's job, is to turn alkenes, or carbon-carbon double bonds, into epoxides. Yep, using MCPBA, we are just going to turn an alkene into an epoxide. So there's our alkene, so we're going to stuff an oxygen in here. Right? So I'm just going to draw my generic structure for my epoxide right there. And now, again, so we're going to have to keep in mind where the methyls are located with respect to each other. So they're on the same side again, so that means they both have to be in the same configuration in your product. Because we now have a stereocenter there once you've stuffed that oxygen in there. Now we have 4 unique things attached to these 2 carbons. Now again, we can draw them both wedged or we can draw them both dashed. Wagner just prefers the wedge because it's easier to, I guess, draw a shaded in nacho than a torn up one. But does that make sense though? Like I said, this one is really tricky if you've never seen MCPBA before. But just make a note to yourself that you're turning the alkene into an epoxide. Like I said, the big hint or giveaway is to look at this cluster of oxygens right here. You're going to be adding an oxygen to your structure. And for alkenes, you're just putting that oxygen right there in the middle that can now be shared by what was once a carbon-carbon double bond.
So you don't need to be familiar with the arrow pushing principle?
Nope, no arrow pushing needed for this guy. So don't stress yourself out trying to memorize the arrow pushing for this. Just try to remember that if you see MCPBA, just know that you're going to be making an epoxide. And that's, for the most part, the extent of what you guys are going to need to know. Because making you guys learn how the arrow pushing for this works is torture. And on a final exam that is, what was it, 24 pages? You ain't going to have time to deal with this garbage. You have to know maybe the arrow pushing for like substitution, and that's about it. So that's maybe one step. This guy is multiple steps with a few intermediates that are very, very ugly and make me hate a certain reaction in OChem, which I hope you guys don't have to deal with it in here, otherwise I'll be very sad. But anyway, any other questions on this guy though? This is just standard, like I said, MCPBA, alkene, give you that sweet, sweet epoxide. Alrighty, let's take a look at the next guy. Alright, so now this one you guys probably haven't seen a whole lot of. Actually, yeah, you guys have seen this guy. Who's this?
That's the H minus.
Yeah, that's sodium borohydride, right? We're going to make that nice H minus, and what's it going to do? Yeah, it's going to falcon punch that carbonyl group down there. It's going to come right down here and be like, bam! Eat my electrons. And what's going to happen once that hydrogen attacks there? Yeah, that's right. We kick these electrons up. The double bond is broken. And then what is methanol doing here besides trying to intoxicate the rest of the reaction? What are we doing with this guy? He's our proton source. So we're making a nice alcohol out of this. But now we can see, judging by the gigantic box, we should have more than one product. How many do we have? We have 2. That alcohol could be on either plane. Again, going back to that, that little white lie that was told to you guys once upon a blue moon. Right? So we could have the alcohol in either orientation. And the orientations of all the other functional groups are not going to change. So, without even labeling any of the stereocenters, we should already know how these guys are related. How are these guys related? These guys are diastereomers because only one stereocenter changes while the others are going to stay the same. And that's it. Any questions on this guy? Like I said, this is a standard sodium borohydride reaction with a nice little ketone there. We use methanol as our proton source, and we get a nice alcohol out of this. But remember, if we want all the possible stereoisomers, that's your big giveaway that you have to draw the alcohol in either one of the 2 orientations. Now, if the box is tiny, like this up here, then you probably only have to draw it with just a standard bond line to it. But a large box like this is your giveaway that, okay, I gotta draw both products or both possible options for that alcohol. Any questions on that one, though? This one, again, this should be gravy right here. This should be easy points. This should be leftovers from Thanksgiving. You guys should be enjoying this. But, makes sense, though, right? Cool? Cool. All right. Well, speaking of gravy and easy points, look what we got here. What's this? Oh, yeah, that's the Grignard right there. The yawn of awesomeness. The Grignard of power. So, and what is this? What are we introducing it to? It's an epoxide, so we're going to be attacking it with our Grignard. Which carbon are we attacking? The one on the ring or the one out here all by itself? The one out by itself, because we want less steric hindrance. So our methyl is going to come along and be like, woo, turkey, and then the oxygen will be like, fuck off, and then it's going to break the bond and it's going to take off. Oh, it comes fun, right? So we end up with this attaching, and what does the oxygen become once we add the H3O plus in there?
OH.
Yeah, it becomes an OH, a hydroxyl. We make an alcohol from this. Again, this should be some gravy points for you guys. We got a Grignard attacking an electron-deficient carbon. You guys have to remember that we're attacking the least sterically hindered side. Because again, that methyl doesn't want to deal with Mr. Fat-Ass Ring over here. It'd rather break the bond out here rather than try to squeeze itself in here in that tight space. But any questions on this guy, though? Typically we see it reacting with ketones and aldehydes, but again, it can attack an electron-deficient carbon that is sitting on the epoxide as well.
When did it attack the most sterically hindered side?
Good question there. So, wouldn't the methyl technically be attacking the most sterically hindered side when we make these? It all depends on the conditions that you're in. Now, if you're using a Grignard or a base, this nucleophile right here is doing the attacking, which is going to be your initial step. But now, if you were under acidic conditions, everything changes. Because then the oxygen is going to dictate where the bond is broken. So I'm going to draw the exact same thing, but I'm going to now introduce an acid to it instead. And that's going to change the entire course of our reaction. So if I added some nice little HCl into this, I'm going to scoot this over so you guys can see. So if we add HCl to this, the oxygen collecting a proton is going to be your very first step. And now once you do this, now we have to ask ourselves, okay, where is the oxygen going to want to go? Now it's not going to want to bounce over here where the ring structure is, it's going to want to bounce outside to where we have less steric hindrance. And then whatever the nucleophile was attached to that acid is going to attach on the most sterically hindered side. But again, this isn't by choice. This is because the oxygen dictates where that chlorine is going to attach. So the only time you attach on the most sterically hindered side, here's Cl and I'm going to put the OH out here. The only time you ever attach on the most sterically hindered side is when you're under acidic conditions. Because again, the oxygen dictates where the bond will break. As opposed to when you're under basic conditions or when you're using a Grignard, this nucleophile attacking is the very first step. So we have to think about what's going to sterically hinder the nucleophile as opposed to the oxygen. The oxygen here has no real say in where it ends up going. The nucleophile takes priority here, whereas over here it's the other way around. The oxygen dictates where the bond is going to